In our first section, 6.1, we're going to be dealing with roots and their associated radical expressions. A lot of you are probably familiar with something basic like a square root of a number, like 5 is the square root of 25. But if I was to say that we can take additional higher orders of roots, so the third, the fourth, the fifth root, call that like a cube root, and then just fourth and fifth root of different values, we can apply that same concept with just bigger powers that we deal with. You can also deal with those bigger roots. So that, again, kind of just using that pattern, defining that we could just use something we call an nth root. If I was to take 5, 6, 7, 8, 9, 10, just kind of keep that pattern going forwards. And for any root of a number, we do see a pattern with if I have an odd or an even root. And that's by saying that if I have an odd root, there's only going to be one real nth root. So let's say like a third or a fifth or a seventh root, there's only going to be one of those. Except if I have an even root, we're going to have two possibilities, so two real roots if I have an even. And that could be, again, for example, like a square root. I could take a principal square root and just leave that as my positive answer, or I could take the negative of that, and that's going to be my second of my two possibilities. If I try to take the even root of a negative number, though, so imagine trying to take like the square root of -4, we know that there's actually not going to be any real roots of that value. So if I was just to try to find the real roots, again, we have pieces of our radical expression here with an index inside the little crook of that radical sign, and the radicand is the value inside the radical itself. So if I was to find the cube root of this decimal, 0.2027, a way to express that would be I'm looking for the cube root of 0.027 as the value. And again, kind of like how we deal with powers, we're just thinking if I'm looking for the cube root of 0.027, we're looking for the number that multiplies by itself 3 times to end up with that value that is inside that radical symbol that we call the radicand. So I believe if I take the value 0.3, we know that 0.3 raised to the third power is going to give us that same decimal that we started with, 0.027. And again, if I notice that this is an odd root, since I'm using 3 as my index, I know that this is going to be the only possible real root for that. That would just be 0.3, because again, if I multiply that by itself 3 times, we end up with that value that we started with. You can also use this as a fraction. So let's say if I was to take the cube root of 64, so cube root of 64, and also the cube root of 125, we could find those in 2 separate pieces. I know that 4 times 4 times 4 is going to give us 64. We also know that 5 times 5 times 5, that's going to give us 125. And again, since we're dealing with a cube root and it's an odd, we know that that's going to be the only real root there. I could also do the same thing with something larger like 343. We could think, again, the cube root of 343 will be the number that's multiplied by itself 3 times to get 343. Maybe you want to guess and check on this one, but if I was to do 7 times 7 times 7, that does give us 343. So it looks like if I was to find this root, it looks like 7 is going to be my only cube root there because, again, we're dealing with that odd index. If I'm looking for square roots in that next section, is where we have to remember that there's going to be 2 possible answers for each now that we're dealing with an even root. Again, square root would just be an index of 2. So for our first example, if I'm trying to find the square root of 49 over 81, I know that just like our previous example, we can look at each of those pieces of our fraction separately. If I was to take a square root of the numerator, 49, I get 7. If I was to take a square root of the denominator, 81, I get 9. So if I was to take those square roots of the numerator and denominator, I know that 7 over 9 would work as one possibility. But again, if I was to also take negative 7 over 9 and think of squaring that same value, that will be another way that I can get that positive 49 over 81. So just like we've seen from our definition from above, if I do have an even root, that means I'm going to have 2 possibilities. We're going to have, the positive and the negative of those. If I was trying to take a negative, so again, in this case, if I had something like negative 0.16, want to find the root of that. This would be a case where I don't have a real square root, again, because of our rule from before. If I was to try to take the square root of a negative value, we just aren't going to have any real roots. If I was to take the square root of a positive, that's what would get us back to our 2 solutions. So trying that last one, if I was trying the square root of 121, this would be another one that you may already be familiar with, but 11 squared gives us 121. But since I'm able to also square a negative 11 and get that same value, that implies that we do have 2 real roots for that. That would be the positive and the negative, 11, negative 11. So if we're trying to explain why, in this last case, that we didn't have a real root if n was even, and again, that would be like a hidden 2 if I was taking a square root in that radical symbol. The explanation I came up with, and you guys can have something similar, is that if I was trying to use that thought process that we're looking for numbers multiplied times themselves to get even number of powers, or yeah, in this case, like a square power, I know that a negative number multiplied by itself, if I multiply an even number of times, it's always going to be positive. So we saw that with like negative 11 times itself. Even if I was to multiply, let's say something simpler like negative 2 times negative 2, that's going to give us 4. If I multiplied it again, so 4 times negative 2, that's going to be a negative. So again, if that's an odd number, I could end up with a negative value. But if I would need to multiply that one more time, so negative 8 times another negative 2, that's going to give us a 16. Every time I do multiply an even number of times, we are going to get a positive result. So next section is just a few more examples of that very same concept. Again, if I'm looking for a cube root, this would be an odd root, so I should only have one answer for each. And if I was to find all three of those, again, if I'm looking for the number that multiplies by itself 3 times to give me that value, 0.2 raised to the third power would give me that decimal 3 decimal places, so 0.2 is my cube root. And then if I was to use a fraction, same idea as from before, I could look at the numerator and the denominator separately. 3 times itself 3 times gives us 27. 4 times itself 3 times gives us 64, and that gives us 3/4 as an answer. Again, notice that we don't have a negative answer here, because if I was to use a negative and an odd number of times, that would actually make my final answer negative. So that's why, again, there's only going to be one solution there, 3/4. If I was to take that last example, kind of like where we saw 7 to the third power gave us 343, 8 to the third power gives us 512, so 8 would be the only cube root for that last one. And now if I want to find fourth roots, we're thinking again of another even kind of power. So if I was to take an even fourth root of these next few examples, that's why we do have two possibilities for these answers. Remember, we do have the positive and the negative. If I was to take 1 to the fourth power, I get 1. Also, negative 1 raised to that same fourth power would give us 1. So that implies that we have two real fourth roots of positive 1. If I was to take the same approach, again, as we've seen with that question from before, can't take an even root if it's a negative value, so I know that there are actually no real fourth roots of my second example. And then if I'm looking at that last fraction, same idea from earlier, I could take 2/3, raise each one to the fourth power, that's going to give me 2 to the fourth, 16, 3 to the fourth, 81, that's the fraction I'm looking for. Or the negative would also work, because again, if I'm using a negative with an even power, that's also going to give us that same positive answer. So I could say on this last one, 2 over 3 or negative 2 over 3, those would both work as my even roots. Now if I'm looking at real number roots, if I was given the root symbol, so cube root on our first example, and even though I don't have an index there, that would be a hidden 2 if I'm looking at a square root of the next example. This is along the same lines of thinking of odd and even roots from before, but now again, I just got to be careful about the signs of my answer. If I have a negative root, I could still take an odd power of that. So if I have something like negative 2 and raise that to the third power, that would be an example that gets me negative 8. So I do know that negative 2 would be that real cube root of negative 8. And if I was to look to that next example, this is something that we have to remember if I just use that square root sign. As we said from before, there would be two possible roots, but if I don't leave a negative or positive sign in front, we're only referring to what we call the principal square root. So we're only looking for that positive answer. If I'm looking at 0.6 as a positive number that I can square and end up with that same decimal in that radicand, this is going to be the only answer I want to use for that, because again, we just said square root. We just want the answer that's our principal root, and that's going to be the one that's positive. If I was trying to find C, this is another example where I'm trying to take an even root of a negative number. I know that just by following my rule, I know that's not going to be anything that we can say is a real number root. And for our last example, we actually want to do this in steps. If I was to solve this basically from the inside out, I can take negative 5 and square that first, so I get a positive 25. And now if I'm taking the, again, principal square root of 25, only using that positive answer, that's just going to give me 5 as a result. We don't want to use the negative root in this case, because again, I don't see that negative sign out in front of my square root symbol. Trying that again with similar examples, see if you guys are able to find these roots as well. Cube root of negative 64 is just going to give you negative 4, kind of like our example above it. If I was to take the even root of a negative number, we should see that this one actually has no real roots that we can say. On our next example, if I'm taking the fourth root of 16, this is again just the positive principal square root, so that would just be a 2 and not negative 2. And then like our last example, D from above, I want to square this result inside my radicand and then take a principal square root to just get that answer to be a positive 8 at the end. So we're very careful about the signs on our last one. We're going to be careful about signs again if I'm looking at simplifying an entire radical expression rather than just simplifying one single term inside of a radical. And that's like saying if I'm trying to simplify this, square root of 81 x to the fourth, all in terms of that algebraic expression, we do want to be careful of this rule that, again, if I'm not wanting to change any values here, we want to make sure if this is even, I'm considering this basically like a absolute value. If I take the same power as the index of my root, and if it was an odd, I just keep the same expression from inside. But again, simplifying that to remove my powers. So the way that this works is if I have a square root and I want to simplify what's inside, we just got to think if I was to take the square root of 81, again, square root of 81, I would have a 9. If I was to take the square root of x to the fourth, this would be x squared. But since I'm to take a square root, this is essentially just rewriting what I have on the inside. If I take 9 and square it, and if I take x squared and square it, I get that original expression. So we're kind of just rewriting this and seeing that it just matches our rule. The index of our root is the same as the power of this expression that we just made in terms of that simplified form. So this is just watching out for signs. That means that since I was taking this as an even power, I know that we're actually using that second rule where I'm looking at the absolute value of that phrase and not just the value by itself. But one thing we can use to simplify this is we know that anything squared is always going to be a positive anyway. 9 is always going to be a positive value. So if I was trying to take the absolute value of that expression, 9x squared is going to end up the same whether or not I have that in that absolute value symbol. On the next one, if I have an odd root, again, if I'm thinking of using those powers and simplifying that down, kind of like we've seen from before, we're just trying to think the third root of a to the 12th power. And essentially you just want to think division. If I just take 12 and divide it by 3, that tells you that if I was to group that in groups of 3, I would have a to the fourth. And same thing if I was to take 15 and put it into groups of 3, I would have 5 of those. So just essentially thinking division. We just want to be able to write these in a form that we start with that property. So we want the, again, index to match the power of that expression from the inside, because now I can see that since this is an odd power, I'm just going to be able to write that as that simplified expression that we're able to get in terms of these parentheses. This final answer, again, just keeping that answer negative because this is an odd power, would be negative a to the fourth, b to the fifth. Again, our powers just basically cancels out with our index, so that's our simplified version of that radical, is just essentially removing that radical expression itself. If I was to try this again, big idea with these kinds of questions when I have these higher exponents is I just think division. Last one, remember we did 12 divided by 3 to get 4. We did 15 divided by 3 to get 5. So if I apply the same process here, again, keeping this written as a radical for now, if I want to find out if I have 12 and I group them into groups of 4, I should have 3 of those. So that would be x to the third. You can always just think 12 divided by 4 gives us 3. 16 divided by 4 gives us 4 powers of y. And again, essentially we're just rewriting this in a way that the index is going to match the power of that expression on the inside of our radical symbol, because now we can apply this property again. Noticing that now that we have an even value, kind of as we saw in that first answer, we're going to have an absolute value in this case of that expression that we're left with on the inside, x to the third and y to the fourth. And kind of like we've seen with our other powers, we know that y to the fourth is always going to be a positive because that's an even power. But in this case, we do have to be careful, and that's why we use that absolute value symbol. If I was to use a negative value for the x, we'd actually be taking an absolute value of that. So since I could end up with a negative answer by using an odd power, I want to make sure that x to the third is left inside of an absolute value sign. So trying that with a few more examples. Again, you just want to be watching out for negative, positive signs and be able to group these down. We know in that first example, again, if I'm thinking the square root of 16, I get 4. If I think of division instead to get my x rather than square roots, either way it would work. But again, 8 divided in half would make that 4. So I have 4 powers if I group them in 2s. And if I was to follow this rule, again, it looks like we're using even power since it's a square root. We know that this would be an absolute value of that expression that I was left with. But the absolute value of 4 is still 4. Absolute value of an even power is still going to be that even power. So this would just be left as 4x to the fourth. The middle one should match the middle one from before. And again, this is like, actually, I guess it's our last example. But if I had this kind of situation where if I, oh yeah, it's an odd power. If I was to take this odd power and think again in terms of division, 6 divided by 3 gave us 2 that was left when I tried to simplify those parts out. 9 divided by 3 gives us 3 when I was trying to simplify that expression as well. And now again, since my index matches the power of that expression, I know I can just use my first rule. I just know that I'm left with that expression and I don't have to use absolute value. So if this is the part that I'm left with, I do just have a squared b to the third. Again, don't have to think about absolute value since we use that odd number for the root. For our last example, should match part C. Again, here you're just thinking division again. 8 divided by 4 gives you 2 powers when I group those for the x. And if I do the same thing with the y's, 12 divided by 4 also gives us 3 powers there. So then if I'm looking to simplify that expression down, we're using our second rule now that this is an even power. These parts that we were able to simplify, x squared, y to the third, that did result in an absolute value. And kind of like the rule that we've seen from before, any odd powers, I need to make sure I leave them inside of my absolute value sign. Any even powers, I can leave outside of that just because, again, we know an even power is always going to be positive no matter what. So you do want to be thinking in terms of simplifying when you divide. Don't have to think too much about like what the individual roots or the individual powers are. I would just stick to that kind of division approach as a shortcut. 8 divided by 4, that's why we have 2 powers left for x. And if you think of division again for the y, that's why I ended up with 3. That was just 12 divided by 4 as well.